Dear students, in the previous classes we have introduced instrumental variable method of estimation as a solution to the problem of endogeneity, that is an explanatory variable correlated with the stochastic error type. Now, to get more insight about why the instrumental variable works, we have to consider the estimation problem as a what is known as method of moment problem. That is, estimation is actually, we can recast estimation as a method of moment problem, or we can derive the least squares estimators as a method of moment problem, and we can derive what is known as the normal equations from two moment conditions. Let us see what is the interpretation of this method of moment estimation problem, starting with a simple linear regression model y is equal to beta 1 plus beta 2 x plus a simple linear regression model. We usually assume that expected u is equal to 0. It means that expected value of y minus beta 1 minus beta 2x is equal to 0. Y minus beta 1 minus beta 2x is equal to 0. Expected u is equal to 0. The second is that x is fixed in repeated samples, or if it is random, not correlated with u. Expected x u is equal to 0 means expected value of x into y minus beta 1 minus beta 2x is equal to 0. Expected x u 0 means expected value of x minus x into y minus beta 1 minus beta 2x is equal to 0. These two conditions are known as the moment conditions. The moment conditions. If we replace these population moment conditions by sample moments, we have two equations in two unknowns, and define the method of moment estimators for beta 1 and beta 2 as, if we replace population moment conditions with the sample moment conditions, we have what is known as the method of moment estimators of beta 1 and beta 2 as 1 by n into sigma yi minus b1 minus b2 xi is equal to 0, 1 by n into sigma xi into yi minus b1 minus b2 xi is equal to 0. And solving this, you will get b2 is equal to sigma xi minus x bar into yi minus y bar divided by sigma xi minus x bar square, and b1 is equal to y bar minus b2 x bar. This is the same as wireless estimators we have derived. So we can think about the estimation of the regression coefficients as a method of moment problem. Now consider this model again. Y is equal to beta 1 plus beta 2 x plus u. Now suppose that expected value of x u is not equal to 0. X is correlated with the u. So it makes the second moment condition invalid. First moment condition is satisfied, but second moment condition is not satisfied. Suppose that another variable zx is such that z does not have direct effect on y and does not belong to the right side. Z has no direct effect on y. That is very important. When x and other variables are controlled, then z has no direct effect on y. Also, z is not correlated, so z has no direct effect on y. Second, z is not correlated with u. Z is not correlated with u, and z is correlated with x, the endogenous explanatory variable. A variable with these properties is known as the instrumental variable. That is, even though z has no direct effect on y, this z allow us to estimate the relation between x and y. It is a tool, an instrument used to estimate a relation between y and x. Even though z has no direct effect on y, z allow us to estimate the relation between y and x. So it is known as the instrumental variable. It is a tool. So if such an z exists, then we can again write the moment conditions as 1. The first moment condition is the same, expected u equal to 0 is equal to, means expected value of y minus beta 1 minus beta 2 x is equal to 0, and expected value of x z is equal to 0 means expected value of z, then z into x z 0 means z into, expected value of z u equal to 0, not x z. Z u is equal to 0 means expected value of z into y minus beta 1 minus beta 2 x is equal to 0. Instead of expected xu, we write it as expected zu. And solving this, you will get the estimates. So the sample moment conditions are written as 1 by n into sigma yi minus beta 1 hat minus beta 2 hat xi equal to 0. 1 by n into sigma zi into yi minus beta 1 plus beta 2 hat xi is equal to 0. And solving this, you will get beta 2 hat as equal to sigma zi minus z bar into yi minus y bar divided by sigma zi minus z bar into xi minus x bar, and beta 1 hat as equal to y bar minus beta 2 hat x bar. These are the instrumental variable estimators. By replacing the second moment condition, expected xu as expected zu, provided that z is not correlated with the x. So we can specify we can specify the estimation problem in terms of the moment conditions. It is more convenient to understand. And Z can act as an instrument if Z does not belong to this equation. Z has effect on X, not on Y. If X is controlled, then Z has no direct effect on Y. Then Z and U are not correlated. Z and X are correlated. That will give us, and population moment conditions are replaced by sample moment conditions. That will give us what is known as the instrumental variable estimators. Instrumental variable estimators. Now, the instrumental variable estimators, as we have discussed in the previous class, are consistent. So, they are consistent. And in large samples, the instrumental variable estimator beta 2 hat can be written as normal with beta 2 and sigma square by r square between Z and X, r square between Z and X into sigma X minus X bar square. And r square is the square of the sample correlation between Z and X. Beta 2 hat is normal with provided that expected ZU is equal to 0. You will get beta 2 hat as unbiased, and its variance is given by the formula. Remember this, the OLS formula is sigma square by sigma xi square. So here there is an additional term. So we can compare this formula with the variance of, this is IV, beta 2 hat as sigma square by sigma xi square. Now as a comparison, variance of beta 2 hat IV is equal to sigma square by r square between Z and X into sigma xi square, sigma x minus x bar square, can be written as variance of beta 2 hat, variance of beta 2 hat divided by r square between Z and X, r square between Z and X. This variance of beta 2 hat is, this beta 2 hat is OLS. Now this comparison invite our attention to the use of, invite our attention to the need for using strong instruments. We know that r square ZX is always less than 1. R square Z is always less than 1. So that the variance of the instrumental variable is always higher than the variance of OLS. The variance of instrumental variable is always greater than the variance of OLS is variance beta 2 hat divided by a quantity which is less than 1. So variance of this instrumental variable is always less than the variance of OLS. Naturally, if you are using the instrumental variable for estimation, then it will result in wider confidence intervals and less precise estimators compared to OLS. As the variance of IV, instrumental variable is normally distributed, instrumental variable is consistent, but remember this, in small samples, the variance of instrumental variable is much higher than that of OLS. So confidence intervals will be wider and estimation will be less precise. Suppose that this R square ZX is equal to 0.1. Then the variance of IV will be 500 times, 0.1 will be 100 times larger than that of OLS. If it is equal to 0.5, then variance of IV will be 4 times, 100 times, 4 times larger than OLS. So the point is, IV estimators solve the problem of endogeneity, but it will give estimators with large variances. And in recent years, a lot of research is going on to analyze the behavior of instrumental variables when Z is weakly correlated with X. Weakly correlated with X. That means when instruments are not strong. And we will see in a later class how to test whether the instruments are strong or weak. Anyway, the point is, when using weak instruments, if you have only weak instruments, then IV estimators can be badly biased even in large samples. Plus, its distribution need not be normal. So if the instrument is weak, it will be biased in small samples, and also its distribution will not be normal. That means confidence interval construction, hypothesis testing, etc. will be suspect. So it is important that instruments are strong. Now the question is how we check whether the instruments are strong or not. That we will consider in a later class. So compare this formula with this. Both OLS and instrumental variable is unbiased. OLS is biased. Instrumental variable is unbiased in large samples, but it is unbiased, but its variance is much larger than the variance of OLS. So it is important that the instrument is strong. Then we have to consider one more issue. We know that after estimating a simple linear regression model, we always calculate R square as a measure of goodness of fit. And R square is equal to 1 minus RSS by TSS, something known to us. Now, unlike OLS, R square from instrumental variable method of estimation can be negative because this RSS can be greater than what is known as TSS. That is a point. So there is a possibility that R square obtained from the instrumental variable method of estimation can be negative. And although nothing will happen if you report R square for IV estimation, it is not very useful also. The reason is that when X and U are correlated, we cannot decompose the variance of Y into, remember this, sigma YA square was decomposed as plus sigma U hat I square. So when X and U are correlated, we cannot decompose this into beta 2 hat square into sigma xi square plus sigma U hat I square. This is not possible. So R square has no natural interpretation in the IV procedure. Now the point is this. If our aim is to produce large R square values, then always use OLS. If your aim is to produce R square, use OLS. Instrumental variable method is used to provide better estimates when X and U are correlated. So, goodness of fit or R square is not at all a factor. The point is, if you use OLS, you will get a high R square, but the estimators are not even consistent, biased and also inconsistent. But instrumental variable, though biased in small samples, is consistent. But R square will not be very useful here. But as I discussed in detail, in regression analysis, our concern is not the fit of sample regression line to the sample data. Our concern is the coefficients, the signs, and the significance. Whether R square is high or low is not a problem. So, if you suspect that in the model X and U are correlated, use the instrumental variable method as a solution. Other solutions are there. We can use what is known as multiple regression model. We can use panel data methods. We can use proxy variables, and many other solutions are there. But if you are using instrumental variable, remember this, R square is not very important as a measure of goodness of it. What is important is how to consistently estimate the regression parameters. This will be achieved by IV rather than OLS. And always remember this, IV has a variance which is larger than OLS, and this variance depends on the extent of correlation between Z and X. If the correlation is very high, then the variance will not be very high. That reminds us the importance of strong instruments, and there are test statistics to determine whether the instruments are strong or not. That is a point which we will see in a later class.